Hello everyone, today's lecture is lecture 3, Dynamic Soil Properties of the module Geotechnical Earthquake and Offshore Engineering. Today I'm going to explain different aspects and elements of the dynamic or the main dynamic properties of the soil and the ground, which I think that you should know in order to be able to understand the correlation between the transmission of the seismic waves throughout the soil and its impact on the infrastructure and different structures placed on top of the surface. But before that, I want to mention that things have been updated on the Moodle site. So as you remember, there were two different Moodle sites, one for the MNG group and another one for the MSc group. And now the two of them have been combined into the title that you can see here in this slide, the XL001535, which is the result of combining the two different Moodle sites. So from now on, this is the Moodle site and that you will have to use, given that I don't think that you have access to any other Moodle site. Again, all the information is here. If there was anything that you cannot access, please let us know. But as far as I am aware, you should be able to watch the videos that I'm going to upload to the system into this website. There have also been some updates on the module delivery, so I decided to change a bit the teaching approach, and that's been because I think that it could be a bit more effective. After the conversation I had with the module leader, Dr. Daniel Barreto, I think that it could be more convenient to do in the next way. So it's been modified and explained in the Moodle announcements, but I can explain it out loud again here for all of you. The idea is that I will be recording the lecture on Monday, and I will try to upload it on Monday morning or Tuesday morning so that you can all access the recordings. And on Tuesday we can discuss about aspects from the previous session. So it will be a bit challenging for you to maybe watch the video and then attend class and be able to answer things related to that session. So what I will try to do is on that session, so for example tomorrow, we will try to cover things that maybe you don't understand regarding lectures 1 and 2 or exercises that you have attempted and you didn't manage to get certain results. So as you can see, that virtual learning environment session delivered on Tuesday from 3 to 6 will be mainly dedicated to discussion, Q&A session. So anything that you want to ask and you need further clarification, that will be the purpose of that session. But it will be more convenient for you and more effective, and we can also put into practice the flipped classroom approach, where you can watch the session whenever you want, and we can use those 3 hours to just share views or discuss and go a bit farther into the knowledge and into the content of those sections that you think that need more information or more input from myself. This is the tentative schedule. As I have shown you in the previous 2 sessions, it's been maintained, so there hasn't been any modification. Today is the 3rd session that I delivered. There will be another 3. Next week it will be about run response analysis. So what I do recommend you to start doing is to download the software Deep Soil, which is available online, and I will provide you with a link for that, because we will try to attempt, if not next week, the following one will be to practice with 1 or 2 simple exercises. After that, the last 2 sessions will be one about local site and topography effects on the wave propagation and its effect on the transmission to the ground surface, and finally liquefaction, which some of you already know about, but we are going to go deeper into the design considerations and aspects we need to consider if we want to protect infrastructure and structures against the liquefaction potential. This is the last slide I'm going to use for showing myself, and that's because, as you can see, the slide has some limited space, so it would be impossible to put the camera inside the slide, and obviously trying to show all the information that I want to give you. So yeah, this is the table of contents for today's class. It's all about soil dynamics and aspects related to the dynamic properties of soils. So first of all, I will do a quick review about cyclic loading and how and where earthquakes sit into this concept. Moving on to dynamic soil properties, trying to focus on shear modulus and damping ratio, strain dependency, how the deformation is affecting the value of these two parameters. And then we will move specifically on to each one of those. First of all, maximum shear modulus, then how the shear modulus is being reduced by means of the modulus reduction curve. What is the damping ratio in terms of energy dissipation, why it is so important. Obviously, the reduction or the change in the curve of damping ratio with a strain will be also explained. After that, an important section which is about experimental testing and the different types of tests that we can undertake in order to get the values of shear modulus and damping ratio of any type of soil found in the ground. And the last section I will go through is a practical study, in this case related to my thesis topic, rubble soil mixtures, which I think is a prime example for showing the changes in stiffness and damping capacity of a soil by modifying the type of soil included into the ground. Among the main references I want you to look into, I will start obviously with Kramer's book about geotechnical earthquake engineering that I've mentioned a couple of occasions already for the previous two sessions. In this case, chapter 6 is all about dynamic soil properties, and I will say that it's self-explanatory. So if you manage to read that chapter, it will provide you a broad view of this area, which I consider it to be a fundamental part of geotechnical earthquake engineering, and that any geotechnical engineer needs to be aware of in order to be able to provide a solution for the design of structures against the transmission of seismic waves. Apart from that, I have also included a couple of references which I think are very complete from the point of view of the content and the amount of experiments undertaken. One of them is Darren Daly's thesis, written in 2001. Another one is Mengs in 2003. The third reference is Harding and Dernovich. Is relatively old, but is widely and worldwide used in the sense that most of the equations that they provided are still being used for calculating shear modulus and damping ratio of certain soils, mainly clays and sands. And then the last reference I've included is my thesis that has been recently included in the repository of the university, and that I do recommend you to go through, mainly chapter 3, 6, and 7, because what I try to do is to simplify the definitions of shear modulus and damping ratio for a specific soil. So if you also want to understand how it is applied to the type of soil, such as the case of rubble soil mixtures, it is a good opportunity for you to go and get some further clarification. Short reminder, until now what we had considered, or at least in the first session, is that for the case of dynamic of discrete systems, a single degree of freedom, which could be the case of a lumped mass such as this one that we have here, could be subjected to a harmonic motion. We then solved the equation of motion and came up with expressions for the relative displacement. Okay. After that, I defined the concept of elastic response spectrum that you have started using for the case of seismo signal, and if you had initiated the delivery and the submission of the formative assessment, you will have seen probably how it works, and the application could be to get the maximum accelerations and the elastic response spectrum in terms of acceleration, velocity, and displacement for different damping ratios. Okay. The problem with this assumption of a single degree of freedom and elastic response spectrum is that we consider it to be rigid. Okay, so we will consider that the ground, the soil that is underneath that lumped mass, is rigid and it doesn't change either the stiffness or the damping ratio. So that will mean that those values are linear and they don't change with the deformation experienced by the soil. And this is not the case. I mean, if we ask, is this the case? Is this the reality? We can say that no, that's not the case, and it is a simplification in order to undertake these simple exercises. So today I'm going to explain how the soil, in terms of stiffness or the ability to deform under external loading and the capacity to dissipate energy, which is the damping ratio, are going to affect the value of acceleration, velocity, and displacement, or the final result on the ground surface as a consequence of the transmission of those seismic waves. Another short reminder for this lecture, and that I think that is worth of noting, is the fact that seismic waves are mainly divided into body waves and surface waves. But what we were really interested into was the propagation of those waves throughout the soil. So first of all, I analyzed the case of 1D road, but then I move on to the case of two soil layers and what it will happen with the wave or the incident wave when it reaches the edge, the boundary between the two soil layers. And the truth was that the displacement and the stress or the energy of the wave will be transmitted and reflected. So there will be a change in the amount of displacement and energy because of that. But not only there will be a change in the amount of displacement and energy, but also in the direction of the wave. So since the moment the rupture of the fault occurs, there is a transmission of the waves in such a direction that if the layers or the soil layers are characterized by a lower stiffness as we move towards the surface, which is this one here, the wave could be propagated in a vertical orientation. So this is one of the main assumptions in the case of ground response analysis when we are trying to consider the interaction between a seismic wave and the soil, is that the wave could be transmitted in a vertical orientation, and is due to this Snell's law. So just for you to bear in mind and to understand this concept that I will repeat next week for calculating the amplification of seismic waves within the soil. In the first session of the module, and then more in the second session, I explained the concept of accelerograms and how the acceleration is being recorded by different equipment. Normally, the case of this acceleration graph with respect to time will be recorded by an accelerogram instead of a seismograph. And if you remember, the difference between the two of them was mainly that the seismograph wasn't able to record strong ground motions. But the question is, would you expect the accelerogram below to change depending on the location where it is recorded? So if we are saying, or we think that the soil is having an influence in the transmission of the acceleration, how do we know that this acceleration is the most realistic or is the most accurate representation of the consequence of any type of earthquake on the soil surface? And the answer is that we need to first of all understand the ground soil, and we need to know where the acceleropgraph is being placed in order to also understand how these values are being recorded. So in a nutshell, what we can say is that acceleration or accelerogram is affected and depends not only on the transmission of the seismic waves, but also on the soil, and you will see how it is affected. It is important to mention at this stage that the cyclic loading, which is considered to be a periodic action, when applied to a material body, then it triggers changes in stress and strain over time. So due to, for example, the application of a harmonic load, then what it's going to cause is changes not only in the deformation, but the strength, or the stress in this case, with time. And that's the difficulty of this area. Then considering that for the case of an earthquake or a seismic motion, that periodic load is even more difficult to analyze, then the analysis of changes in stress and strain become very difficult. Something that I've mentioned before and is worth of repeating is that an earthquake is a typical cyclic loading event in which the seismic waves propagate outwards from an underground source. Another important aspect, and that you will see in the next slides, is that the loading frequency of an earthquake is negligible for the analysis of the soil dynamic properties. That doesn't mean that when the loading frequency tunes with the frequency of the soil, it creates or it leads to the resonance phenomenon. But for the case of the analysis of the dynamic properties, loading frequency with ranges between 0.1 and 20 Hertz is negligible, and negligible. All the inertial effects are negligible. This table that you can see here at the bottom represents the different type of exercises that we will find, for example, for the case of geotechnical engineering, and you can find how some of the number of cycles are very low, for example, the case of a blasting bombing, and they increase in this case with different types of problems. Earthquakes could be included here, pile driving compaction, traffic loads, and machine foundation, which leads to a fatigue wave because of the amount of waves that are being applied to the structure. And then when we move towards this side of the graph, we will move to more static problems, so temporary and permanent structures, parking vehicle load, and wave-induced load. So I think that this graph gives a good overview of different designs and problems that we consider in geotechnical engineering, and among those, and the one that we are more interested in right now, is earthquake loading. This picture is a simplification of the three main stages that we will find in the transmission of seismic waves. So one is more to do with lecture 2, the propagation since the moment that there is like the rupture between the two, well, the consequence of the fall between two tectonic plates, and what happens with those seismic waves. Number 2 could be the transmission within the soil. So we consider this area to be the rock. So in that case, the strains could be very, very low, and there wouldn't be any amplification or barely any amplification of the signal. Number 2 is the moment when it crosses and goes through the soil layers, and that's where the side response takes place, and I'll explain more about this in lecture 3. But before that, in lecture 2, you need to understand how the dynamic soil properties change the value of that amplification, and why it is so important to analyze the concept of soil stiffness and damping capacity. And number 3 could be more to do with the final or the later consequences of that transmission throughout the soil, and how it's transmitted in this case across the surface layer. And that will be more to do with lectures 5 and 6, where I'll explain the side effects and the liquefaction potential. Following from the previous slide, seismic waves travel well through rock, and in that way can cover huge distances rapidly, but the small layer of soil lying near the ground surface can have a very significant impact on the magnitude of the shaking that occurs at the ground surface. So it is worth noting that the wave is transmitted throughout the soil, or in this case the bedrock initially, and it wouldn't really cause any significant deformation or strain around that section, but it's in the last part, the last bit here, where the superficial layers are found. We can talk about the case of clays, sands, any other type of superficial layer that we found nowadays close to the surface, where the seismic wave changes the orientation. It goes to this almost vertical direction, and it causes the magnitude, or the amplification of the magnitude. Okay, so there is an amplification of the magnitude as a consequence of those soil layers that are at the top of the ground soil. So it is important to recognize that the interaction between a seismic wave and the ground is just that, an interaction. The seismic motion, which is generated at a source, consists of seismic waves of a certain amplitude and frequency. So the propagation of this seismic motion affects the properties of the encountered soils, and vice versa. So the soil deposits also affect the characteristics of the seismic motion in terms of amplitude and frequency. So that's important to highlight, is the fact that the seismic wave is transmitted through the soil. It triggers the formation of the soil, but that deformation of the soil, or the properties of the soil, in this case stiffness and damping ratio, are also affecting back the seismic wave. So it's an interaction between the two parts. Today we're going to look at the part which is the soil properties. In the previous session it was more to do with the transmission of the seismic waves, and in the fourth session, lecture 4, is going to be the interaction between the two of them. So additionally, the soil surface controls the transmission, amplitude and direction of seismic waves. So in this case, when it reaches the surface, when it reaches the top of the soil, then there is also a transmission of the surface waves, and that's why the side effects are going to obviously influence the value of that transmission. In this slide, I recommend you to watch the following video, where it is shown the different types of seismic waves propagating through different ground conditions. So you will see that based on the type of ground and the type of seismic wave, the consequences in terms of amplification of magnitude are different. So please have a look at the video, and you will get more information on this area. But based on the knowledge that you have so far, can you infer any information on the impedance ratio? This is important, and is that based on the content from the previous lecture, lecture 2 about seismology and wave propagation, we knew that when a wave is transmitted through a material and then it reaches the boundary between two different layers, there is a transmission of the wave, and there is a reflection of the wave. So in this case, before the wave gets into a soil layer and we need to deal with soil dynamic properties such as shear modulus or damping ratio, we need to understand that if the difference between the properties of the two soils are quite significant, what there will be is a complete reflection of the soil of the seismic wave, and that's what we saw, for example, towards this part of the graph that you can see here at the bottom right, and is that if, for example, the properties, the shear wave, which defines the stiffness of the soil layer above the soil layer 1, is much harder, what it will happen is that most of the energy is being transmitted back, and the same happen with the displacement. The same phenomena occurs when the soil layer above the first layer is much softer than the first one. So the difference in the damping ratio, which is obtained from the difference in the soil properties, is going also to cause before the seismic wave propagates throughout the soil, the reduction of the magnitude or the amplitude of a wave. So something to bear in mind before we get into the detail of soil dynamic properties. The impedance ratio is important to understand what happens with the seismic wave at the edge between the two, for example, soil layers, if we are analyzing the two of them. But the idea is what happens afterwards when the seismic wave enters the area of a soil layer and is transmitted through that soil layer. For that, what we need to analyze and obviously elucidate is the value of the two main dynamic soil properties, which are G, the stiffness, the shear modulus, this one here, and the damping ratio, which represents the capacity to dissipate energy represented by the word psi. So from the engineer's point of view, for calculating those two dynamic soil properties, we need to first analyze and obtain the value of two variables, which are well known by all of you, I can imagine. Shear stress, the shear deformation of any type of soil under the action of a specific type of loading, and shear strain is the shear deformation, or represents the shear deformation of a soil under the action of loading. So in this case, those two variables are going to be the consequence of any type of soil or material being subjected to dynamic loading, specifically to any type of external dynamic loading. And from there, what we obtain again is the value of G and psi, or damping ratio. So a soil subjected to symmetric cyclic loading may exhibit a hysteresis loop as shown below. So this graph that you see here, bottom left, is let's say one of the most common graphs that you're going to see, and probably you've seen in other references, which represents again that relationship between the shear stress and the shear strain. The inclination and the breadth of this loop are of importance here. So first of all, the inclination of that loop depends on the stiffness of the soil, described by the tangent shear modulus, which is this one here. Whereas the second shear modulus, G-sec, is the average over the entire loading cycle. So we are going to calculate the second shear modulus as the ratio between that point there and that point there. And that will represent the inclination of the hysteresis loop, and it represents the capacity of the soil to deform under certain external loading. So for G-sec, this is going to be obtained as the ratio or the division between the change in the maximum value of the shear stress with respect to the value of the shear deformation. So again, remember that the two variables of importance, shear stress and shear strain, are the consequence in terms of stress and deformation of subjecting any type of material, or in this case the soil layer or a soil that we are investigating about or trying to find more information about, under some sort of external dynamic loading. Apart from the inclination of that relationship between the two variables, we also need to look at the breadth of the loop, which is related to the area, and it's a measure of the energy dissipation, also described by the word psi or damping ratio, and it's the equation that you have probably seen in many references before in Kramer's book. Is also found in many chapters. What that equation will represent is the ratio between the maximum dissipated energy, the maximum strain energy, which represents the stored energy inside the material, and area of the loop is the area of the hysteresis loop. So I will further explain this with more detail based on the information that I will show in the following slides. But it's important to understand that the broader is this hysteresis loop, the more energy is being dissipated by the material. Some useful notes is that G-sec, or the second of the shear modulus and damping ratio, are often referred to as equivalent linear soil properties, and significant attention has been given to the characterization of the two values or the two dynamic soil properties. However, bear in mind that an equivalent linear response is an approximation of the non-linear behavior of the soil. So it is expected that the soil behavior is a function of the applied strain, as it is presented in the sequel in the next slides. So until now, if we analyze the case of, for example, a single degree of freedom system, we will only consider one value of the damping ratio or the damping value, and one value of the stiffness. But this is a simplification. It is not true that a soil could be characterized by a single value of the stiffness or the damping ratio, but it will change depending on other factors, on other elements of the soil, and that's what I'm going to explain in the following slides. Still, if we want to undertake an equivalent linear analysis, and that will be the first step for you to understand the interaction between seismic waves and the soil, we have to consider that those two values are constant. I've shown you in the previous slide the relationship between shear stress and shear strain, and that will represent the stiffness. But the stiffness is simply defined as the measurement of the resistance of a material to deform under applied loading. So we will say that the higher the stiffness of a soil, the more in this case, the less likely it's going to suffer deformation under any external loading. So we will consider a soil, or the bedrock, for example, we will consider it to be with or characterized with a very high stiffness, whereas the case of, for example, some clays will be characterized with low stiffness. So in this case, stiffness changes govern the switch in a material response under load from a small strain deformation to large strain deformation. So the higher the stiffness, the less likely it's going to suffer or to trigger the deformation of the soil. This distinction is hugely important in soil mechanics, as it forms the basis of the distinction between elastic and plastic material behavior. In this case, the stiffness of soil is represented by the shear modulus G, which I've shown before, when they are subject to external dynamic load and seismic motions. So in the next slides, what I'm going to show is the strain dependency, the factors in terms of strain deformation that are influencing the value of the shear modulus, which are obviously which are the basis for understanding the concept of elastic and elastoplastic material behavior of any soil layer. The first factor to consider when we study the change in the values of the dynamic soil properties could be the volumetric state variable. So in this case, that's represented by the value of the shear strain, and it is commonly known as the strain dependency. So we know that strain ranges are defined in relation to material behavior, and the first stage of the material behavior could be allocated for the case of very small strains. So we are talking about very small deformations, and what happens with the two dynamic soil properties at those very small deformations. So when the cyclic loading of a soil generates very small strains, behavior is considered to be linear elastic. So only at that stage where there are small deformations, we can say that the values of stiffness and damping ratio are linear elastic, and they don't change with deformation. So soil properties do not change during loading. Main points to bear in mind is that damping ratio is constant and typically very small. Shear stiffness is constant and equivalent to GO or G max, and I'm going to tell you more about that value, how to calculate it for different type of soils. And this behavior is adequately captured by a two-parameter elastic soil model, so it could be G max or the damping ratio. So in this case, and only in this case when there are very small strains, then we can say that the two values of G and chi, or the damping ratio, are constant. But we are talking about deformations of 0.001 strain, and thus in this case obtain, for example, a shear stress of 50 to 100 kilopascals of stress. Let's say that in this case, obviously, the stiffer the material is, the less it's going to deform, and in this case it will be common to think about the analysis of the linear elastic analysis when we talk about very stiff soils, and in only in those conditions where the deformation is very small, we can talk about constant values for the damping ratio and the soil stiffness or the shear modulus. Only that. So just consider that when you are thinking of the dynamic soil properties. The next stage in the range of the strain dependency could be the area between small and medium strains. So let's say that at that stage, when there are more deformations, so let's say that because of the action of any type of cyclic loading or any type of harmonic load, imagine that there is an increase in the value of the harmonic load, then it triggers a series of deformations, in this case in measured as shear strain. So the soil behavior remains repetitive but non-linear elastic. So let's say that we enter a elastoplastic area where there starts being a deformation of the soil, and it cannot be considered to be elastic anymore. So this behavior implies that the soil's shear modulus will vary with cyclic shear strain amplitude. So the shear strain dependency of G max is better appreciated in the set of graphs that are shown here. So what happens is that when we look at the relationship between shear stress and shear strain, there is a moment where, in this case, this graph is no longer straight, and it starts to curve here, and that's what we call the backbone curve. And there, where would you try to represent the value of the change in the stiffness with respect to the maximum value, what we find is that with the deformation, with the shear strain, the value or the maximum value of the stiffness reduces. So this is the typical graph that you are going to find, is that with more deformation applied to the soil, the stiffness decays, and that's something that is quite important at this stage for you to understand, and we cannot consider to be that property to be elastic or constant anymore. So again, the backbone curve, or what we call the backbone curve, could be this curve that you can see here at the top, bottom left graph, which reaches a maximum point. So we say that the backbone curve is the locus of points corresponding to the tips of hysteresis loop of various cyclic strain amplitudes. So its slope at the origin gives us the value of G max. So the ratio between the value here at the origin with that value is represents the maximum stiffness. But then when we increase the strain amplitudes, so if we increase the value of the deformation from that point where the maximum stiffness is found, then the value of the stiffness drops lower than the unity. So we call that the correlation between the shear modulus ratio with the cyclic strain is also called as the modulus reduction curve, and is the one that you see here. So this graph here on the right is representing how the value of the stiffness changes with the value of the deformation. So normally the characterization of the soil stiffness is not only shown by the value of the maximum shear modulus, but also the reduction in the value of the soil stiffness with respect to the maximum value, in this case with the deformation. So this graph that you have here on the right is going to be seen in the following slides, and you need to understand that in this case is representing what is the value of the stiffness at any stage with respect to the maximum value. So when the deformation is very small, the value is the maximum value, so that's the maximum soil stiffness that the soil is going to be characterized with. But as we apply more forces to the ground and there's more deformation as a consequence of those forces, the value of the soil stiffness will reduce or will decay. The main difference between the previous section in the strain dependency, which is between small to medium strains, and this one, medium to large strains, is that as we apply larger shear deformations, the value of that curve that I showed you before, the ratio between the stiffness and the maximum stiffness, continues to change, and further shear modulus degradation occurs. Okay, so there's a higher reduction in the stiffness with respect to the maximum value. Among other consequences, we find that the breadth of the hysteresis loops tends to increase with increasing the cyclic strain amplitude, which implies that the damping ratio will also increase. So the value which represents the dissipation, the energy dissipation capacity, will increase with the deformation, which is the opposite to what happens with the soil stiffness. Then it is also common that the volumetric strains accumulate, and then hysteresis loops tend to become flatter, and of a smaller area with the number of cycles, as you can see here. So as we apply more and more cycles to the soil, what is going to happen is that graph becomes flatter, and obviously that represents that there is a change in the soil strength. It is losing part of the particle interaction until it finally fails due to the accumulation of volumetric strains. Finally, modeling this behavior requires of an elastoplastic material that solves the equation of motions over time. So this is nothing to do with the elastic analysis, and we will need of fully dynamic model in which the stiffness and damping ratio are functions of a stress of modulus reduction, and I will mention a couple of them that you can see in some specialized and specific software, such as the case of FLAG or Plaxis. Hence, here you can see a comparison between the three areas of the strain dependency and its effect on the value of the stress-strain relationship. So you can see here shear stress, shear strain. The graph that you find here at the top left represents that small strain by means of the red line that you can see here in the center of the graph. So there will barely be any change in the soil stiffness as you apply more and more cycles. But then if you move towards the maximum value of the soil stiffness that it can reach as a consequence of the deformation, then as you apply more and more cycles, there's going to be a reduction in the soil stiffness, and then that's obviously seen at a higher magnitude for the case of very high strains. So I don't know if you see here that the breadth of this hysteretic loop is quite broad. So let's say that there's a high dissipation of energy. So in this case, applying higher deformation is going to cause a higher energy dissipation. But it's also true that the value of the stiffness is decaying, which is represented by this line that you can see here, and it's becoming more and more flat, to the point that when it reaches the value of 0 is when we consider that there's no resistance of the soil to the cyclic loading. So what will happen is that all the particles lose their strength, and they are not able to withstand any additional cyclic loading applied to the soil. So obviously this could be a critical point for any housing or soil foundation, given that obviously it wouldn't be able to support any further strength or application of loading, and it will fail eventually. The figure below summarizes the different strength ranges together with expected changes in shear stiffness. So again, going back to the ratio between the stiffness which is being measured compared to the maximum value of the stiffness, we find the three zones: very small strains, small to medium strains, and then larger strains. So we will say that some of the exercises of design that we will consider for this module and geotechnical engineering will be in this range. It will be mainly between medium to large strains, retaining walls, foundations, tunnels, conventional soil testing. So it is true that by means of the testing that we will normally conduct, these are the values of stiffness and consequently the values of the damping ratio that we can measure. And I will also explain that by means of other forms of experimenting and testing the soil, we can also calculate this part of the graph, because if not, what will happen is that we will lack of all this information that we can see here. The next table is showing a summary of the different effects of the magnitude of strains on the soil. So as we move towards this part, we will find magnitudes of 10 to the minus 6, which is considered to be a small strains. Whereas when we move here, we will talk about large strains and obviously more severe consequences. So we have wave propagation and vibration. As we move towards larger strains, we will find cracks and differential settlement as the main phenomena of soil consequences, and then we'll move towards slide, compaction, and liquefaction. In terms of mechanical characteristics, we will say that on the left side, the behavior of the soil can be characterized as if it was elastic. We'll move to elastoplastic and then failure. It is also important to consider other factors, such as the effect of the load repetition or effect of rate of loading. And then here you can see a summary of the main in situ measurement tests for calculating the properties in each one of these ranges, and the laboratory measurements, such as the case of, for example, bender elements, resonant column tests, or cyclic triaxial testing more towards the area of medium to large strains. The value of the maximum soil stiffness is directly correlated to the shear wave velocity, as we saw, for example, in the last session. And what we know is that based on the calculation of the shear wave velocity, Gmax, or as I was saying, the maximum soil stiffness, is going to be equal to the density of the soil times the square value of the shear wave velocity. So we can obtain that value from various lab testing and also empirical expressions, which have revealed the dependence of this value upon different factors. So depending on the type of soil that we are analyzing, in this case, if it's more cohesionless or cohesive soils, such as the case of clays, there will be different characteristics and different factors which affect the value of the maximum soil stiffness. As you can see in the table at the top, there is a series of factors that we have to take into account depending on the type of soil that we are considering. So for the case of sands, we will look into relative density, confinement pressure, age, cementation, fines content, over consolidation ratio. But if, on the other hand, we are considering clays, we will take into account other factors such as void ratio, natural water content, overconsolidation ratio 2, confinement pressure, H, and plasticity index. So again, that's something that we will know beforehand based on the references and the bibliography that we have. But it is proven that the value of the maximum stiffness of a soil increases with increasing the next few factors, which are confinement pressure, H, cementation, OCR, which corresponds to the overconsolidation ratio, and the plasticity index. On the other hand, the value is going to decrease, so the soil is going to be less stiff, or the maximum stiffness is going to be lower with increasing the strain rate, so that's deformation, void ratio, and number of cycles. The next slide presents a series of equations that have been proposed as empirical correlationships in order to calculate the value of maximum soil stiffness for the case of sands or cohesive soils such as clay. So for the case of maximum soil stiffness of sands, we have the equation proposed by Harding. In this case, this equation will depend on factors such as void ratio, that, if you remember, could be the ratio between the volume of voids and the volume of solids. And then you also have atmospheric pressure, or the mean confinement pressure, which is the pressure at which the soil is being subjected. Then there are other equations, such as the one proposed by Sid and Idris in 1970, or the one proposed by Harding and Richard in 1963, more typical or more used for the calculation of soil stiffness of a typical sand, which is the Leighton-Buzzard sand, commonly used in the UK. As you can see, the structure of these equations is not too different. The only difference could be the use of other constants. For the case of clays, the main difference is the addition of the overconsolidation ratio factor as a factor that is affecting the maximum value of the soil stiffness, and that can be calculated with the equation that you have here in the middle right side of the slide. There is another equation proposed by Jamiolkowski in 1991, which follows the same structure than the previous one, but with other constants, as you can see here. There's more information that you can access about the calculation of these empirical correlationships in the table 6 of Kramer's book. This will be a typical table or graph that we will find if we try to calculate the maximum soil stiffness, the G max of certain sands. In this case, you can see that the units are different than the units that we will normally use in Scotland. So it will be pounds divided by square feet. But still, you could create a correlation with our own units. What is interesting about this graph is the fact that the value of K2, which is then included in this equation, the common equation proposed by Sid and Idris, is also affected in its turn to the value of the relative density of the soil. So apart from the factors that are included in that initial equation, the relative density, the percentage of density with respect to the maximum density of that study soil, it will also have an effect on the value of the maximum soil stiffness. The following slide is showing the correlation between the ratio of the stiffness divided by the maximum stiffness, which is known as the modulus reduction curve, with respect to the shear deformation, in this case represented by the shear strain. So as you can see here, as we apply a higher deformation to the soil, the stiffness is going to reduce. So the value, for example, 0.6, which is found here, takes place when the soil is being deformed above the value of 0.01% of the shear strain, and this represents, this point here in terms of shear strain would represent a 60% of the total value of G max, which is the maximum soil stiffness. So anything beyond this point will obviously mean a reduction of the soil stiffness, and that's the common case for most of the soils. When soils suffer from any type of deformation, the stiffness as a consequence of the cohesion of the particles drops and that would be quite variable depending on the type of sands or the type of soils that we are analyzing. So I don't know if you can see here that there is a range of values. So this will correspond, for example, to different type of sands, and other factors such as the ones provided before will affect how far it is in this, let's say, range or area of different points, different values that can be included within those two upper and lower boundaries. As I proposed at the beginning of the presentation, there are two references that I would recommend you to go through in order to have and get a grasp of what it would be the modulus reduction curves for different soils. One of them is the thesis written by Darendelli in 2001, and the other one is Meng's thesis written in 2003. What is interesting about these PhD dissertations is that Darendelli relied on an extensive database of soil samples, which range between natural clay sands to clays characterized by a wide range of sampling depth, confinement pressure, plasticity index, and overconsolidation ratio. So they created a series of equations which are based on statistical analysis of obtained lab data. Following a hyperbolic type equation, it suggested that the value of the ratio between the soil stiffness and the maximum soil stiffness would be equal to this equation that you can see here. This is very common when you are trying to understand the reduction of the stiffness with a shear deformation, and this equation actually fits pretty well with the experimental values that you will find for sands and clays. Within the equation, there's a series of variables that you need to consider. One of them is the reference shear strain, which is the value at which the soil stiffness is half of the maximum soil stiffness, and Darendelli suggested that value would be around 0.03%. You will find that in some soils that are considered to be more likely to deform under external loading, that value will increase, and the value of alpha will be around 0.9, but that will change depending on the type of soils that you are considering. For Meng's investigation, it related the above parameters with uniform coefficient CU that you studied in soil mechanics and the confinement pressure. So in this case, the value of the reference shear strain is obtained by a series of the equations, as you can see here in front of you, depending on the uniformity coefficient, the confinement pressure, and this factor that can be calculated with other equations here. So this again, I do recommend you to read some of the sections of this thesis, because you will understand how the normalized stiffness modulus curves will change with different factors. Here's an example of what it will happen with the modulus reaction curve, the ratio between the stiffness of the soil divided by the maximum stiffness. And I don't know if you see here that in this case, in the top graph, which only represents the value of the stiffness of the soil, the value of a well-graded gravel is much higher than a poorly graded sand. Okay, so the maximum value of the well-graded gravel, which is a different type of soil, could be higher than the poorly graded sand. However, when we try to look at the reduction in the stiffness with respect to the maximum value as a consequence of the shear deformation, which is represented here, the case of the poorly graded sand, given that it's more compacted because of the let's say similar size of the particles, it results that the reduction in the value of the stiffness takes place at a lower pace. However, on the other hand, even though the value of the well-graded gravel is higher at the beginning when there are low deformations, such as the one that we see here, as we deform the soil, given that the level of compaction is lower, the particles lose the strength much more quickly. And as you can see here, with the increase in the shear deformation, the reduction in the maximum soil stiffness takes place at a quicker pace. So it happens in a faster way than with the poorly graded sand. What you see here are a couple of graphs which correspond with empirical curves for non-plastic soils written by or provided by Ishibashi and Sang. And the one that you have here is the correlation between stiffness and the maximum stiffness, and the one at the bottom is the damping ratio. And I don't know if you see that, for example, for the case of the stiffness, as we increase the atmospheric pressure, which is represented with that line that you see at the top, the value of the stiffness is higher, to the point that in some cases when the deformation is high, the value is higher than even the initial or the maximal soil stiffness, and that's because of the degree of compaction of the particles due to that increase in the atmospheric pressure. For the case of the damping ratio, the process is the inverse. So what happens is that at low pressure there will be a higher dissipation capacity, which is the one that you see here, and this corresponds to an atmospheric pressure of 0.25. Whereas as you move along the graph and you increase the atmospheric pressure, particles are more compacted and close to each other, and the dissipation capacity will be lower. Among the different factors that are changing the value of the soil stiffness, soil plasticity is significant, probably more so than void ratio, tending to reveal a pronounced increase in stiffness with increasing the plasticity index. If you remember, the plasticity index will be calculated as the difference between the liquid limit and the plastic limit, and you did some experiments in second year in soil mechanics for its determination. So it can be also seen from the figure below that the linear strain threshold increases with plasticity. I don't know if you see here that it's very clear that as we increase, or the soil is characterized by a higher plasticity index, the reduction in the soil stiffness with the deformation is much lower, so it happens at a slower rate. So if we did a comparison of the shear strain threshold, which is the value when the stiffness is equal to 0.5, the maximum value of the stiffness, it will happen that the linear threshold, it will be moving towards the right. So what it represents is that the soil is passing from being a more plastic, or having a more plastic behavior, to a more elastic behavior. So the translation in that value of the threshold, of the linear strain threshold, will obviously be it will mean, or it will be reflected on a more elastic behavior of the soil. As I was saying before, shear modulus of high plasticity soil degrades at a lower rate compared to low plasticity soils, and we can see clearly here. This line here will represent a very high plasticity soil with respect to this line that you can see here. So if we compare the value of the soil stiffness at 0.1 of the formation, we will find that the soil stiffness of this type of soil characterized by that plasticity would be around 0.20 something. However, on the other hand, if we compare that value to the one of a highly plastic soil such as this one, we will find that it has barely lost the initial stiffness, and we will be in the range of 0.9. So that's a big difference between the correlation in the modulus reduction curve between the two types of soils. So it is extremely important, as it can influence the soil response. It passes from being a more, let's say, a more plastic behavior to a more elastic behavior, and it determines if a soil deposit will amplify or it will attenuate earthquake motions. One of the main factors also affecting the change in the modulus reduction curve as the ratio between soil stiffness and the maximum shear modulus is the confining pressure, sigma m. And in this case, there is a big difference between a low plasticity soil, such as this one, where the increase in the confining pressure is going to result in a compaction of the particles, and then obviously as in an increase of that ratio, which means that the degradation of the shear modulus happens at a lower rate than, for example, a high plasticity index soil or a very plastic soil where the change in the confining pressure is barely having an effect because of that high value of the plasticity of the cohesive soil. So particularly for soils of low plasticity, the effective confining pressure becomes more pronounced, and that implies a slower degradation of the shear modulus G. The modulus reduction curve is represented in the next slide as the correlation in the graph between G and G max with respect to the shear strain with the effect of the number of cycles. So as you can see, the dashed lines will represent the value of that modulus reduction curve with only one cycle, and then all these lines that you have here, they will show what will happen with the soil stiffness as we apply more cycles. So repeated cycle loads tend to degrade the stiffness of the soil. The stiffness degradation is more intense at lower PI value, so as the soil presents a lower plasticity, the stiffness degradation is higher with the number of cycles. But it is affected, or the reduction in this value of the stiffness with respect to the maximum stiffness is affected more by a variation in plasticity index than by the cyclic degradation. So what it means is that it is more important the value of the plasticity index than the number of cycles that is being applied to the soil and how that affects the change in the soil stiffness. One of the two main dynamic soil properties that we need to be aware of in order to understand how the seismic waves are transmitted throughout a soil layer of certain characteristics is the damping ratio. And to create a distinction between the first lecture and this one, we say that to describe the energy consumed at a material point, we use a different type of damping than the viscose damping that we came across in lecture 1 about single degree of freedom system. In this case, when we talk about damping in soils under external cyclic loading, we talk mainly about hysteretic damping. And hysteretic damping is nothing but the mechanical energy lost as a consequence of particle friction and the sliding between particles. So normally hysteretic damping will be correlated to the soil non-linear behavior. One difference between the two types of dampings, in this case the viscose damping, which is normally found, and this is interesting, at small strains. So we will say that at small strains, the main type of damping that we will find even in soils, not only in the single degree of freedom system, could be viscose damping, is that viscose damping is frequency dependent, whereas the hysteretic damping is independent of the frequency of loading. So we say that in this case, hysteretic damping is therefore independent of the frequency, which is a familiar characteristic of soft soils, particularly granular materials. Why it is so important to understand the concept of damping ratio is because if no damping existed, then an initial perturbation or excitation will trigger an indefinite oscillation of the material or object in question. So what we say is that in reality, damping attenuates oscillations, bringing the object eventually to rest. So if the damping ratio of any type of soil was equal to 0, then what will happen is that any wave, any energy transmitted throughout the soil would be amplified. There wouldn't be any loss of energy, any dissipation of energy. However, the fact that some of these soils possess a very high damping or energy dissipation capacity is what results in the attenuation or in the reduction of the perturbation, and we will see how the different factors affect the value of the magnitude of a damping ratio characteristic or variable. As a means of calculating the damping ratio associated with a certain type of soil, we need to understand the different components of that equation. So we have here at the top left is the typical relationship between shear stress and shear strain that we've seen since the beginning of the lecture. And what we see is that this dotted section within the two, well, in this case within the hysteretic loop, which represents the loading and loading cycle at which any, in this case, the soil is being subjected to due to the external loading, is representing this inner part. Okay, so that part which now is being shaded by myself, that will represent the amount of energy which is lost per cycle of loading, equivalent to the area of hysteresis loop. So that will be the energy that is being dissipated as a consequence of the properties of the soil. So it is also called the damping potential, and it is related to the magnitude of the applied shear strain, and it's not entirely a material property. So in this case, the value of the hysteresis loop, or the amount of energy that is being dissipated, is this one that you can see here. And that will be a function of the viscosity of the material, C. It will be a function of the frequency of the system, and it will be a function of the displacement or the strain. But then that value of the damping potential, or the energy dissipated, is being related to the maximum amount of strain energy stored, which occurs when the strain is at its maximum value, and given here by the triangle W. So in this case, this second equation is which represents the triangle under the value of the maximum shear stress and shear strain, which is this one that you have here. So it's the one that I'm coloring right now. So that value will represent the maximum amount of energy that is being stored under that hysteresis loop. So the relationship between the two of them will represent the damping ratio, and the damping ratio normalizes then the energy dissipated by the maximum amount of energy stored. And this is the typical equation that you have seen in other books. So in this case, if the value of the energy dissipated was very close to the value of maximum energy stored, will mean that the soil is dissipating most of the energy that is being stored within the soil. So the higher the value, the more energy is being dissipated with respect to the energy that is being stored. And on the other hand, if the value is low, it means that the soil is barely dissipating energy, and it is mainly being stored by the soil. What we see here is a representation again of the large strain and small strain hysteresis loop with the shear stress and shear strain I showed before for the strain dependency situation. And what we say is that in theory, at strains below the linear cyclic threshold shear strain, there should be no hysteretic dissipation of energy. So that means that if there is an obviously a plastic behavior, if the soil is not being deformed under plastoelastic conditions, and there's not being volumetric strain deformation of the soil, then there cannot be any dissipation of energy, and that's what happens normally at linear conditions at small strains. However, experimental evidence has shown that some of the energy is being dissipated even at very low strain levels. So the damping ratio is never zero, and that's because here there is another type of damping which needs to be considered, which is called the material viscose damping, and is dependent on the viscosity of the soil. So that's why at very small strains, another type of damping, which is not the hysteretic damping but viscose damping, needs to be adopted, and is more related to the linear elastic conditions of the soil and the viscosity, the vibration of the soil due to the viscosity of the soil, and it can only be found in very specific experiments with resonant column testing, and I'll show you how it works later. Based on the damping ratio definition, the greater the applied shear strains, the greater the value of damping ratio that we see, and the area of the loop increases. So it makes sense that if we subject the soil to a higher deformation, the soil is dissipating more energy because the particles are under more pressure. There's been more friction between the particles, and that's what is causing the deformation and the dissipation of energy. Is the friction between those particles, is the sliding mechanisms between the particles. So as the stiffness reduces, the value of the damping ratio will normally increase. Therefore, as shown for the case of the modulus reduction curves of soil stiffness, there is a direct link between the damping ratio and the applied shear strength. So there are also curves to define the evolution in the damping ratio with the shear strength, as you can see here. So this is the percentage of damping ratio, and this is value corresponding to the shear deformation. And as you can see, there is also an upper and lower range of values that we are going to see depending on the type of soil and depending on a series of factors. This graph is representing the value of the damping ratio for various types of sands, in this case as a collection made by Sid and Idris from previous authors. And as you can see here, the value of the damping ratio of different sands is falling into different parts of the graph within those upper and lower ranges. So we can see that, for example, for the case of 0.1%, some values of some type of sands will have a damping ratio of around 20% or 21%, whereas all the type of sands, for different reasons, it could be the confining pressure, it could be the plasticity index, will have a 9% of damping ratio, or it could be characterized by a 9% of damping ratio. That will mean that it will have the capacity to dissipate energy than all the type of sands, and that's probably one of the main objectives when we are testing the soils with the use of different experiments, is to know the value of the percentage of the damping ratio associated with that type of soil. And as you can see, the general trend is that the value of the damping ratio will increase with the shear deformation. This slide corresponds to the slide I showed before about the effect of the confinement pressure on the soil dynamic properties. I said before that the value of the soil stiffness will increase with the value of the confinement pressure, whereas for the case of the damping ratio, the value will be reduced. So it's completely the opposite effect. What happens in this case is that the particles are too close to each other. Because of that, confining pressure is causing the particles not to be able to displace and result in the energy dissipated as a consequence of the friction. So in this case, the higher the confining pressure, the lower the amount of energy that is being dissipated by the soil. In this case, we are talking about non-plastic soils. In the following slide is presenting the proposed curves of the damping ratio as a function of the plasticity and obviously the shear deformation, and we can see that the trend lines is completely opposite to the trend or to the behavior presented for the case of the modulus reduction curves of soil stiffness. And in this case is that by increasing the plasticity index, the value of the damping is being reduced to a higher plastic behavior of the soil will result in a lower dissipation of energy, because of the lower capacity to obviously, like, the particles are not able to slide and to create the friction between them, and that will reduce the total amount of energy that can be dissipated. In the same way that Daly presented a series of equations for the modulus reduction curves of the soil stiffness based on that analysis of the different type of sands and clays under different circumstances by changing the overconsolidation ratio, the plasticity index, and the confining pressure, he did the same for the case of the damping ratio and proposed a series of curves based on an equation that will modify the one presented by Mason in 1926. So this is the equation that has been adjusted or modified based on the one that you can see here. So this equation that you see at the bottom is presented by Mason almost 100 years ago, and that equation is the typical one used by different type of software and ground response analysis software for the calculation of the damping ratio. In this case, Daly decided to adjust that equation because there were some limitations in for example, the value. It wasn't able to provide a value of the minimum damping ratio at small strains, and it will adjust it in such a way that it will accurately fit to the experimental values presented by Darren-Deli. In this case, in the equation, we can find that the normalized shear modulus is being introduced, and there are other factors such as the actual value of the shear strain, reference strain, curvature coefficient, the small strain material damping ratio that needs to be calculated experimentally, and there are other factors that can be seen in his thesis, and that I will recommend you to read if you want to know more about how that equation is being adjusted. So we say that the parameters B and D minimum, which is the minimum damping ratio, are a function of the soil type and loading conditions. This next slide is showing that the value of the minimum damping ratio proposed by Darren-Deli could be correlated to other factors such as the plasticity index, over-consolidation ratio, and in situ mean effective stress and loading frequency. So these are the graphs that will be normally used for obtaining the value of the damping ratio or the minimum damping ratio for a specific value of plasticity index, a value of the mean confinement pressure, and also for the value in this case of the overconsolidation ratio, which is the one that you can see there. So by relating the three of them with the minimum damping ratio, we will be able to add an empirical result to the analytical relationship by means of this equation to provide a value of the damping ratio. As for the case of the minimum damping ratio, Darren-Deli also proposed a series of graphs and curves for correlating the reference strain with the overconsolidation ratio, plasticity index, and the confinement pressure, and the scaling factor B correlated to the number of cycles to which the soil or the material that we are testing is subjected to. So in a nutshell, what Darren-Deli proposed is a series of analytical relationship equations that will provide a value of damping ratio and also the reduction in the soil stiffness with the factors that he studied, and that it will provide the basis for the comparison with experimental testing, also to double check and to show the difference between experimental testing and analytical relationships. These two graphs that we can see here represent the value of the modulus reduction curve, which is the one at the top, and the change in the damping ratio with the shear deformation, with the shear strain, which is the one that you have here at the bottom. And they are calculated, or they have been obtained analytically based on the series of equations that I've introduced it to you before. So you can see that he's used the value or the A factor equal to 0.92. The shear reference strain has been around the value of 0.212, and from there also he decided to add the value of minimum damping ratio, which is the damping ratio at very small strains, and the value of equal to 60.62 due to the number of cycles applied to the soil. So this could be obviously the result or the final step in our calculations of analytical relations, and that we'll be interested in obtaining if we want to test and carry out a ground response analysis. And in that case, we are not only considering linear constant factors of G and D, but also we want them to change with the shear deformation, because we want that analysis to be more realistic. What I've decided to do here is to give you a series of useful remarks that I think that you need to take into account when you are designing the modulus reduction and damping curves for a specific type of soil. So imagine that you were trying to come up with the equation of the change in the soil stiffness and the damping ratio with the shear deformation for a type of soil. This could be the type of exceptions or the type of rules that you will consider, given that each one of the family of curves presented by these authors have or present limitations. So what I do recommend you to do is to go through them and compare it with the equations and the graphs that I've shown before. But just as a general advise every time that you are trying to come up with the modulus reduction and damping curves, read this and obviously consider which will be the range or the zones where you can use the equations presented. Some practical information or overview of the dynamic soil properties has been presented here. It is obviously a summary of what I've explained before, but the truth is that the main, let's say, information is that soils exhibit, in general terms, non-linear and elastic stress-strain behavior under cyclic loading, unless they are subjected to very small strains. So we say that at low strain levels, the stiffness of a soil is the greatest, so it shows the greatest values, whereas the damping is the smallest. And obviously, as the value of the strain or the deformation increases, the nonlinearity and the inelasticity is shown. So that's the reason why the soil stiffness will be reduced in such a way. So G divided by G max, and this could be the shear deformation, and the damping could be the highest, and it's because of that deformation, it's because of the friction and the sliding between particles where it's causing the increase in the damping capacity. So a complete characterization of the above response is complicated, and for the great majority of engineering applications, approximate solutions are adequate. So the truth is that if we try to capture the nonlinear behavior of a soil with all the factors to take into consideration, it could be very difficult to represent and to simulate, and that's the reason why some models or constitutive models are used for as a means of simplifying the process. The first one that we will see, and I will explain next week, for the ground response analysis is linear. Then another one that is commonly used and is very typical in cases like, for example, 1D analysis in deep soil would be equivalent linear. We have also cyclic nonlinear analysis and advanced constitutive models, which could be more complete and more challenging to produce. To compare the main characteristics of the different type of models that we could use in order to characterize the behavior of the soil under the action of seismic loading, we have three main types, which is, first of all, the equivalent linear model, in which the soil could be treated as a linear viscoelastic material whose nonlinear behavior would be characterized by a set of modulus reduction curves and damping curves with respect to the shear deformation. In this case, we say that the equivalent linear model is a bit more advanced than the linear model, because in the linear model we will have a constant value of the stiffness and the damping ratio, which could be too simplistic, but is not as advanced as the cyclic nonlinear model, which in that case makes it a bit more manageable and easier for the user and the person who doesn't want to get into the difficulty of the cyclic nonlinear models, which is the second one shown here, which represents a bit more accurate nonlinear and inelastic behavior of soils using a nonlinear backbone curve and a set of rules that define the unloading reloading behavior. So we call them to follow non-Mason rules. If you remember, Mason rules were the rules that could be used for defining the loading and unloading behavior, and that follows more an elastic behavior of or plastoelastic behavior of soils. The third type of models could be the advanced constitutive models, and are the most accurate method, but the most complicated as well. They will rely on three different types of situations. One of them could be the yield surface, where the limited stress condition for which the elastic behavior is observed. The hardening law that it is, for example, used in Plaxis 2D, which describes the changes in the size and shape of the yield surface as plastic deformation occurs, or the flow rule, where relate increments of plastic strain to increments of stress. Those type of constitutive models could be very advanced, have been produced and in this case distributed by some companies, and they are specific to the well-known behavior of certain soils. The truth is that if we don't have the whole range of dynamic soil properties of any type of soil layer, it would be difficult to come up with such an advanced constitutive model. But it is good to know that they are available at a commercial site. Just as a recap, this is the information concerning the values or the different factors that will affect the maximum soil stiffness or shear modulus of a soil. So we will have the reference strain, the void ratio, confinement pressure, plasticity index, over consolidation ratio, and the number of cycles. And that I mentioned before is that for the case of non-plastic soils, the effect of the confinement pressure is more pronounced than for plastic soils. For clays, we need to also take into account plasticity index, overall consolidation ratio, confinement pressure, and the number of cycles. And the shape of the modulus reduction curve is influenced more by the plasticity index than by the void ratio. Now, I'm going to move on to the type of testing and experimental data that we can collect in order to obviously cover as much information as possible for the case of the soil dynamic properties. And we said that experimental data can come from laboratory or field testing, each with merits and shortcomings. For the case of lab, we are talking about control testing circumstances and sample characterization. So in some occasions, the sample will be disturbed, whereas in case of in situ testing, there will be no sampling, so avoidance of sample disturbance, so there will be obviously the sample wouldn't be disturbed. Representation of large areas, poor water drainage is no control, but it will allow only the in situ conditions to be tested. The main soil properties of interest in a cycling investigation would be these four that you can see here: stiffness, damping, Poisson's ratio, and density. But the first two are the most important properties and can be obtained from a variety of tests, which may be classified according to the strain range and or location. Here we have let's say the combination of field tests which will be used or based on the concept of wave propagation. I mentioned them in the lecture 2 when I was explaining about the measurement of the P wave and the S waves, and we said that by measuring the speed of travel waves, it will mainly establish the elastic parameters. So the first of them could be the seismic reflection, and is most useful of large scale and or very deep stratigraphy. It's rarely used for the delineation of shallow soil layers, and is used to evaluate the wave propagation velocities and layer thickness of superficial layers. The second one is the seismic refraction. In this case, it involves the measurement of P and S waves arrival time, so it gives P and S wave velocities, easier to analyze than the reflection test, and I explained about this case in the previous lecture, and it's the one that you have here at the top on at the bottom right. The third one is the Rayleigh wave test, and is used to indirectly infer the S wave velocity based on measuring the Rayleigh wave phase velocity. Here we have another two field tests that are worth of reporting, and again is to measure small strain tests. So we are talking about the transmission of body waves or surface waves across the surface and throughout the soil in order to measure aspects such as thickness or S-wave velocity of the soil, which will represent some of the mechanical properties of the soil. So the first of them is the spectral analysis. Well, in this case, this is the fourth one, is the spectral analysis of surface wave. So it then identifies the thickness and S-wave velocity by matching dispersion curves. It is quick, no need of boreholes, and can detect low velocity layers up to a considerable depth, up to 100 meters. And the fifth one that we are going to find in this section is the seismic cross hole test, which uses two or more boreholes, and it is represented in the figure that you have here at the bottom right, to measure wave propagation velocities along horizontal paths. So it is effective in proving hidden layers that may be missed by refraction surface. With regards to the laboratory tests that could be normally adopted for the calculation of the dynamic soil properties at small strains, we find first of all the case of the resonant column test. So for example, here the picture at the bottom left is the one I took when I was in the Bangalore institution in India, and that was for calculating the stiffness and damping characteristics at very small strains of rubble soil mixtures by subjecting the sample to torsional or axial loading. So in this case, we are not talking about in situ test on the soil, but just characterization of a sample. The second one that is commonly used is the Bender element test, and what it happens is the piezo ceramic plate vibrates to transmit shear waves through the soil sample, and then what it will do is to calculate the time that it takes for the shear wave to go from one end to another end, and by doing that we will be able to calculate the value of the G max. In this case, I will say that the Bender element is one of the most useful equipment or laboratory test for the calculation of G max, because it provides an accurate value of the maximum soil stiffness of the soil for certain type of soils. I would say that is more convenient for cohesionless soils. Moving on to the range of medium to high strains, we find that in the case of field test, there is a common one, which is the standard penetration test, also known for the acronyms of SPT, and it corresponds to the number of blows, in this case the value n, to achieve a 30 centimeters penetration, and that's correlated to the shear wave velocity. If you remember, maximum shear modulus will be obtained as multiplying the density times the shear wave velocity to the square. In this case, the value of n is a function of soil type, confinement pressure, soil density, and is also influenced by the test equipment and procedures. On the right, we have a graph which represents the statistical correlation between the shear wave velocity and the number of blows obtained by means of the SPT test. In this case, this strain range covers the volumetric strains in drained state or pore water pressure generation in undrained state. For the case of the SPT test, the test procedure has been shown here, so I would recommend you to go through the test, because it gives you the different indications and the different guidelines that one should follow in order to carry out the test. Something that again is worth of reporting is that the value or the M values will correspond to the last 300 millimeters of penetration, whereas the first 150 millimeters is not used as affected by disturbance. So as a means of trying to reduce the possible disturbance at the beginning of the use of the test, of the SPT test, we will just take into consideration the last 300 millimeters. The figures that you can see here on the right, top and bottom, are representations of the equipment that we will normally use for carrying out this test, and also the procedure and the different measurements that are needed and are required for the test. It is also known that for the case of the SPT test, the results are sensitive to numerous variations and numerous factors. So these are some of them. We will consider, for example, method of drilling could have an impact on the final result, the diameter of the drill hole, type of hammer. So just as a purely informative summary of the considerations that one will need to bear in mind, go through them, read them, and compare them with any other type of reference of bibliography that you may have and that you want to obviously know more about. Given that there are so many factors and elements that may have an impact on the final value of the result for the case of the SPT test, what is normally undertaken is a correction of the M values. In this case, is known as N60. So the SPT N values are corrected for field procedures, and I don't know if you see here that there are a series of variables that you need to include into the equation, such as the case of hammer efficiency. You also find the borehole diameter correction, sampler correction, road length correction, and obviously the actual value that you've measured of the SPT N value. And all those corrections are applied to the value of N and then divided by 0.6, which means that actually the value that you will find could be larger as a consequence of divided by that 0.6 in the end. In this slide, a couple of tables have been presented for you to have the information in order to account for those corrections in the final value of the on the blows of the standard penetration test. On the left, you can see the SPT hammer efficiencies depending on the type of hammer. And then on the right, you can find a borehole diameter factor, CV. You can also find the sampling method factor, which is CS, and the road length factor. So depending on the type of the length of the road, there will be a correction to apply to that equation. So these tables are essential for you to obviously apply those corrections once you knew the value of the number of blows that you after carrying out the test and dividing all those results by 0.6. One of the last corrections the geotechnical engineer should action would be the correction for overburden stress. So it is said that the SPT data can also be corrected for overburden pressure to compensate for the effects of the effective stress. So in this case, in order to apply the correction, we will need to get the value that have been previously corrected, N60, from the value of the initial value of N, and then that will be multiplied by the square root of 100 kilopascals divided by the effective stress. So in this case, obviously, if the effective stress could be too high, then what it will happen is that that value of N60 will be reduced. So in this case, this is one of the last corrections that one should apply to the value of the number of blows by means of the standard penetration test. Apart from the calculation of the shear wave velocity based on the number of blows of the SPT test, also we could include correlations to the relative density, the shear strength, and the undrained shear strength, as you can see here in this case. But one thing to bear in mind in this case is caution is required, as these correlations are empirical and should be used with caution and conservatism. So what it is said here in this case is that normally the values obtained from the SPT test could be correlated to all those parameters or properties that have been described before. In this case, relative density, shear strength, and undrained shear strength. But those are based on empirical correlations and no pure experimentation of the soil. So we need to be careful with using those values as valid and accurate to the behavior of the soil. The second most common type of field test could be the cone penetration test for analyzing the dynamic soil properties at or in the range of medium to high strains. Some of the most common characteristics of this type of test could be the use of two different types of cones, mechanical and electric cone, and by means of using a hydraulic ram, what we will obtain would be the cone resistance, which is the total force acting on the cone divided by the projected area, and the cone side friction, which is the total frictional force acting on the friction sleeve. So by calculating those two values, we are able to obtain the friction ratio as the ratio between the two of them, which is typically high in cohesive and low in cohesionless soils. Here there is a list of the most important advantages and disadvantages, and among the most important advantages is that by means of using the cone penetration test, we can obtain retrieved data continuously with depth, so we can trace fine changes in stratigraphy, and with CPT tests can be performed about 4 times faster than SPT and relatively inexpensively. They can be unreliable or unusable in soils with significant gravel content, and sometimes no soil sample is recovered, so cannot inspect the soil. The graph that you see here represents the correlation between the cone resistance with the normalized friction ratio, which is the ratio between the side friction and the cone resistance. And as you can see here on the right side of the slide, there are different zones which represent the behavior of different type of soils. So as we move along the legend and we will increase the number, it will pass from being a more, let's say, cohesive and less stiff soil to a more stiff soil, such as the case of, for example, gravelly sand to sand, sand to clay sand, more cemented or over-consolidated soils. Whereas like when we move towards the left side of the graph, where the value of the normalized friction ratio and the cone resistance will represent a more, let's say, soft type of soil. So in the case of, for example, number 2, we are talking about organic material that will be characterized by a very low shear strength, for example. This has been based on the information provided by Robertson in 2009, which provides a whole range of interpretation of cone penetration tests as a unified approach. So I do recommend you to read it if you want to know more about the results and the correlation between the shear wave velocity, which is the one represented here, with respect to each one of these values, the normalized cone resistance and the normalized friction ratio. Among the different types of laboratory tests that I am aware of and you should know about in order to test the dynamic soil properties of, in this case, any type of soil within the area of geotechnical engineering, but in the range between medium to high strains. The first of them, or the one that I've used in the past, is the cyclic triaxial, and I'll show you later on what we can obtain from it. But the truth is that with this one, what we are doing is adapting the static triaxial rig to a more cyclic axial loading. So this could normally be used for the range of high strains more than medium strains, but still you can also carry out tests in the medium strain range. What we will do with this test is to provide a confinement pressure around the sample, so it will be under the same conditions that we will find it in the ground soil, and then the rig creates or applies that cyclic loading by maintaining a frequency. In this case, we will normally use 1 Hertz of frequency, but you can increase it or decrease it as you wish. And from there, what we will do is to change either the shear stress, or you could do the test based on a fixed shear strain. So by doing that, what you will look for is to get the values of the shear modulus and the damping ratio at specific values of the shear strain. So it could be the case of, let me show you. So it could be the case that maybe you want to look at the value of G and D at specific values of the shear strain, in this case 0.05%, 0.1%, 0.2%, so that you create a graph where you will show the different values of the reduction in the modulus curve as G divided by G max with respect to the shear strain, and the same for the damping ratio. But again, I'll show you how it works later on for the with the investigation of the rubber soil mixtures. Just to mention that there are another 2 types of equipment that will be able to provide information regarding the dynamic soil properties by means of lab testing in the medium to high strain range. One of them could be the cyclic direct simple shear, probably you've seen it in the past. Less common than the cyclic triaxial, but it will be able to represent more accurately the stress state induced by earthquake loading. And the second one is the cyclic torsional shear test, which is most commonly used to measure stiffness and damping characteristics over a wide range of strain levels, which will be represented by the image that you have here at the bottom right. If you want to know more information about these types of testing, please let me know, because I can provide some guidelines and some manuals. Still, if you try to find look out for more information about any type of field or lab test, there's plenty of information available online, so I do recommend you to take a look if there's any type of equipment or test that you want to know more about. Just to conclude with this presentation, I want to go through the main elements and information of a practical case study. In this case, it was the topic of my PhD dissertation, which you can access here if you want to know more about. And I do recommend you, because there are some specific experimental testing and results that are directly related to this lecture. and it was the topic known as rubber soil mixtures for the mitigation of earthquake building damage. So as the name says, the material used was the rubber soil mixture, obtained from combining recycled rubber tires with Layton butcher sand, which is a typical type of sand that we will normally use for investigation here in the UK. And the truth is that we found a gap in the knowledge. We knew that tires were used for different purposes, but they weren't being used in the area of civil engineering. So there was a whole market that could be exploited in that sense if we wanted to make use of that waste material and we wanted to reuse it for some purpose. And we found out at the beginning that the material could be combined with different type of soils. We knew that in the literature it had been used in the past with other type of clays in some institutions and universities in India. So the whole purpose of combining the two of them was to create a more deformable, a more flexible material that when added to the soil will be able to mitigate, to attenuate the action of seismic waves before reaching the ground surface. As part of the practical implications of this study, we came up with a question which could be: how does the introduction of rubber soil mixtures into the soil foundation modify its earthquake response? So the main idea was to add the rubber soil mixture in the form of a layer, and in that way we will alter the dynamic soil properties of the ground soil, and in turn what we will do is to change obviously the interaction between the ground soil and the seismic waves. So for that we thought of two different let's say placement or two different design of the soil foundation. One could be as completely horizontal layer, and the second one will be added as retrofitted rubber soil mixture columns. For the case of the rubber soil mixture layers, there could be a limitation, is that the house or the structure could be constructed afterwards, so after the addition of this material, whereas the case of the retrofitted columns could be also applied for the case of existing buildings. So since the beginning we were thinking about the practical implications of the use of this mixture, but for that prior to any use of practical any practical use of the material, we needed to understand the soil characterization and the dynamic behavior of the soil under certain conditions. To characterize the dynamic soil behavior of this let's say novel material, the rubber soil mixture, we had to carry out a series of experiments in the small to medium strain range by means of using resonant column tests, which are taken at the Indian Institute of Science in Bangalore. And the second set of experiments was conducted at Edinburgh Napier University by means of using a cyclic triaxial test with our new cyclic triaxial equipment, and you will see what we can obtain with the two set of experiments. The two experiments correspond to the field of lab testing that I've explained before, and that you can read more about in the thesis if you want to understand how it works. These are some of the most important graphs obtained from that characterization of the soil by means of the lab testing. One of them could be the normalized shear modulus with respect to the shear strain, and the other one is the damping ratio with respect to the shear strain that I've explained in the module, in the lecture content. In this case, by adding rubber, the increase in the percentage of rubber will transform the soil behavior into a more plastic behavior. So what it will happen is that at high percentages of rubber within the mixture, the sample will be less likely to suffer from the stiffness degradation. For the case of the damping ratio, we found that with the increase in the percentage of rubber, there will be an optimum value, and in this case it was around 10% of rubber soil mixture, that it will lead to an increase in the capacity of the sample to dissipate energy, and that's because of the combination between the particle sliding with the deformability, with the change in the volume of the rubber particles, which added the two of them will cause that increase in the damping capacity, which is effective, which is beneficial if we want to add this material into the soil in order to attenuate the impact of the seismic waves when they go throughout the soil. Just to finish with this part of the practical case, another aspect that I wanted to investigate about the change in the dynamic soil properties of the mixture was to see the modification or alteration in the shear modulus G or damping ratio with the number of cycles. And this is important because you need to bear in mind that when we are talking about some strong ground motions, some of them will last for 30 to 60 seconds. So we are talking about a significant number of cycles applied to the soil before the seismic motion finally stops. So in this case, the number of cycles is something that is being underlooked in the past, evaluated, and we wanted to know more about for the case of saturated samples of rubber soil mixture. What it was really interesting from the point of view of the soil dynamic properties is that at very small percentages of rubber, so we are talking about sand, what it will happen is that after a few cycles the sample will eventually liquefy and it will lose entirely its shear strength, so it wouldn't be able to withstand any load applied to the sample. However, as we added rubber, 10% in this case, 20%, the sample will be able to resist the cyclic loading for many cycles. And in the case of, for example, 30% of rubber added to the Leighton Buzzard sand, it will withstand a 1% of shear strain, which is a very high value, for over 400 cycles without suffering from liquefaction. So that's very beneficial if one or someone wanted to add this material into the soil to resist the action of an earthquake. For the case of the damping ratio, something similar happened, is that sand fail in the end because of liquefaction, so there will be a reduction in the capacity to dissipate energy because of the loss in the interparticle friction. But with the addition of rubber, even though there was still a reduction in the damping capacity, it will maintain its ability to dissipate energy, which is obviously crucial if we wanted to introduce this mixture into the soil. So as you can see, in a very summarized way, we can understand the characterization of the dynamic behavior of a soil by carrying out a series of tests, and this could be the first step prior to putting the sample or the material in place and obviously conducting other type of field investigations. But before that, we need to really understand how the soil stiffness and the damping ratio change with other elements, other factors, such as the case of shear deformation, over consolidation ratio, confining pressure, or number of cycles. So this is it for today. As you can see, the session has been a bit long, and that's because this area of soil dynamic properties will take a bit of time to explain and to look at each one of the cases of factors that influence and alter the value of the shear modulus and the damping ratio. Apart from that, I've also been able to explain some of the empirical relationships that we will use for the calculation of G and D. And we've gone through the main laboratory and field testing that we'll be adopting nowadays in order to calculate the values of shear wave velocity and in turn the value of the shear modulus. If there was anything that you want to ask about any of the references, bibliography presented, or the information that has been added to the content, please come to the virtual learning environment session that will be shared every Tuesday between 3 and 6 p.m. So yeah, and that's it for today. I hope to see you next Tuesday. And again, if you need any extra help, please let me know and send me an email as well. Thank you.